review. I know this stuff, this Hess's Law stuff, again, guys, even talk, some of these are in office hours. I'm like, yeah, we had it in high school. And let me just try to summarize the big picture. One of my favorite reactions, and phase is important. I'm not tempted to put a Hess's Law question on the exam because it takes up a lot of space. And all I'm doing is checking. I'm going to include numbers for like liquid oxygen versus gaseous oxygen. That's the kind of way I would trip you up with that. And at the same time, that's just kind of low level and foolish, so I don't really want to do that. Again, it takes up a lot of space on the booklet, so I don't want to do that either. So I'm not leaning towards a Hess's Law question on the exam, but regardless, you do need this because we're going to get into a lot more complicated things as you actually figure out how far a reaction goes, because even in high school, hopefully you were sophisticated enough to know that even if delta G, I think I have delta H is minus 890, but whatever. Delta G is obviously clearly negative for this reaction. Just because you have a negative delta G, you know it's spontaneous, does not mean the reaction goes to completion. And we're going to cover exactly how and why, and to the point where you will calculate how many products you have over reactants. You're going to do that with the reaction quotients, which you might remember from freshman chemistry. But unfortunately, it's one of those things that we gave you a simplified. The way we told you to do it was simplified to the point of being wrong, like a lot of things in this class. A lot of things not in this class specifically. Anyway, that's what we're building up to, and of course you've got to be able to do Hess's Law to start that calculation. Okay, big picture about, again, this high school level, in terms of calculating the things, yes, calculator, high school, but just want to remind you that the big picture isn't that you get the Gibbs energy of CO2 plus the Gibbs energy of H2O. Of course, we'd have to multiply that by 2, minus the Gibbs energy of methane. And I shouldn't even finish writing this out because it's just childish. But anyway, Gibbs energy of O2. I better multiply that by 2. This would work if I could tabulate the Gibbs energy of all these chemicals. It's just that we didn't, because this is too hard for reasons I went over. So let me just remind you of that. So I'd have a delta G of this reaction, STP. STP, okay, I kind of see a true or false question, 25 degrees Celsius, 1 bar pressure, blah, 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 blah. Anyway, so we figured that this was too hard. So what we did instead was, because of the first law, we actually expressed all this. Oh, why didn't I give myself some room? Sorry, I didn't. I should have gave myself a little bit of space here. Instead, what we did was we tabulated not the G's, but the formation G's. And this ends up giving us the correct answer, the exact same answer. And that's because of the first law and everything is relative. So if I spit this out and give you the delta G and delta H, and what you're not seeing is that that this and whatever number I have for that actually comes from elements that form CO2. And again, whatever this delta G is, that's the delta G of formation in the table in the back of the book. And on top of that were the elements that in their standard state that form H2O. And then there's a delta G for that, but multiply it all by 2, right? We covered that last time. And now what we have to do is subtract out for O2. So normally these are, okay, and I'm being an idiot, that one's a null reaction, right? Again, maybe that's a true or false question. And then I have CH4, and that was formed from its elements. So I have to remember that the delta G I see in the table in the back of the book, I put a minus sign in front of that. And what happens is that all these elements, due to conservation of mass, all of them will cancel. And that's what you're seeing here. So yeah, that's the big picture. Again, their high school level thing still works. Products minus reactants times stoichiometric coefficient. That won't screw you up. But all of that still works. But this is just a little bit more than nuts and bolts about how and why. especially because we've been talking about U and H, and now I've got something different, but it was just done for convenience, and everything's fine because of conservation of energy, the first law. And remember that, so Hess's law is the thing that says we can add these up, but remember that's not real. I don't know why we even, nothing against Jermaine Hess. He was a circus clown, I think I mentioned that before. But nothing against him, but it's just a statement of the first law. I don't know why we let him have a law. Let's see, I guess, okay, now what else did I talk about? Again, so that's the big picture. Okay, then I don't even feel like cleaning this up here because it's just too stupid, really. Next thing we covered was, and I was going a little too fast at this point, was, oh God, what is that? Kirchhoffs Law, which states that when you want to change the temperature, instead of figuring out the new H or the new G of every one of those products and reactants, what you do is you calculate, to get, let's say that you're doing the H, what you do is you have delta H at T1, we're going to make that 298, that's why I put a little circle there. And what you're going to do is correct for the heat capacity, where this is the change in heat capacity of products minus reactants. Now, the big picture is I've actually gone through and looked at all the numbers. Remember that you can change, you can figure out the new delta H, the new delta G of all your products and reactants individually, and then do products minus reactants and get the new delta H, the new delta G at the new temperature. That is totally fine. But as a matter of convenience, instead, if you just subtract the heat capacity of products minus reactants and then just do this one step, you see that's why it's easier. Just do this one step, it gives you the right answer. Mathematically, it's identical, it's just a lot easier. You're skipping, you're not really skipping steps, it's like you're factoring them so that you don't have to add up so many things, you just multiply. Anyway, so it's just easier, that's the big picture. And remember that entropy, I didn't write this down last time, but this is why I cover gases first. So the change in entropy of a reaction would be the standard state. But of course, it works a little differently in that instead of delta T, I have the natural log of T2 over, and again, I'm just going to remind you that I'm not going to play any tricks with T1. I'm going to make it 298. I have to because of that little circle right there. I'm not going to play games with that. And then what you do is you take delta H T2 minus T2 delta S T2, and that's how you get delta G T2. Sorry, this is one I just write that down, just in case, because you have to do it on the next homework. Delta G at T2 will be delta H at T2. Notice I'm not writing a little circle. What could mess you up is if you forget that that's a T2, delta S at T2. Again, no little circle because we're not at standard state because we're at a different temperature. And yeah, and okay, so yeah, you're going to do this you're going to calculate delta G and delta H at different temperatures. But there's two different ways to do this. Is the hard way to do this. But let me show you, remind you about the Gibbs-Helmholtz equation. Gibbs-Helmholtz also calculates delta G over T at different temperatures, but there's a real subtlety to that, and it's actually part of your homework. And, oh, you're going to hate me for this. My answer key, the derivation's a page long, so good luck with that. Normally things are thrown at me, but so because it is a biz knocker, I'll go over exactly what's on the homework because otherwise I think it's really not that bad. It's just that when you're doing the Gibbs-Helmholtz equation, and I'm trying to get you to understand this a little bit better than what I just covered, you're going to find that as you're doing the derivation, you will hit a page and you're going to be like, what? I thought he said that we don't do this. Not that time. Okay, so remind you of the Gibbs-Helmholtz equation that the change in delta G over T was delta minus delta H over T squared, and dg dt dt. Sorry, I'm just doing this off the top of my head. And then, of course, if you want to do this practically, what you would integrate is delta G over T. The limits would be the change in delta G over T. And over here you've got minus delta H over T squared dt. Okay, this is the way you would do that. And I've done this before. I'm just reviewing. What you end up with is delta G at T2 over T2 would equal, you got delta G, one delta G minus the other, so I'm just going to bring that over. I'm just doing a step. And I'm also working with the fact that T1 will be 298. And this would be plus, again, I remind myself, delta H naught, again, that's at 298 times 1 over T2 minus 1 over 298. Okay, again, integrate this, recognize, yeah, it's not hard. I've gone over this before. Okay, now the trick is, and again, I'm basically giving you one of the answers, is to note that delta G naught is delta H naught minus T delta S naught, minus 298 times delta S naught, 298K times delta S naught, sorry, I'm using the board too well. Okay, and then what you get from there, again, this is what I'm asking you to do on the homework, is delta G at T2 is delta H naught minus T2 delta S naught. Okay, so then this is what you get when you do this derivation. What am I saying? I've basically done it for you. I just didn't do the algebra right here. And the point here is that look how different, okay, these look the same right here, but where they're not the same is that this thing is actually that monster up here, and this thing is this monster right here. But notice that's not true here. So what the heck? And this is why I asked this on the test, because I kind of clued in that I've seen some texts do it this way, and then they talk about Kirchhoffs Law, they do it this way, and I'm like, well, they're not the same, right? Simplification to the point that something's wrong. Okay, now, actually the answer to this conundrum, why is this not exactly this? This is clearly a high school level simplification. It actually is occurring right here. Can any of you tell me what's wrong? So there's an approximation made right here that trickles down, an approximation, and remember, that's a controlled mistake, a mistake that results in this not being this. What is the approximation being made from here, obviously, to here, right? What is it? Anyone want to hazard? Okay, notice that you're integrating 1 over minus 1 over x squared, which is what? 1 over x. 1 over x. All right, and what happens to delta H? It was treated as a constant. Does delta H change with temperature? Yes. Right. So this, when you see this derivation, it might even be in your book, and it leads to this expression. I did a little extra algebra to show that it's actually this, which is really in a gross approximation. The gross approximation occurs from here to here, where delta H was removed from the integral, when it should not have been. Okay, so you're going to walk through this and show me this. This is the easy one, especially because I just did it. Here's where you're not going to like me too much, all right? But if you do this, all right, we're going to still do delta G over T. Okay, is the integral of delta H, but what you're going to do is you're going to note that delta H changes with temperature by this T minus 298. Sorry, I came out kind of screwed up. Okay, so this is the temperature dependence to T. To H, sorry, to H, right? Okay. Right, now I'm letting H change with temperature. Sure, this guy is still not affected, but guess what? This is going to do a lot of stuff. And when you do that, and then you insert, okay, so you do the calculus, which is 2 or 3 steps, and then you insert delta G at 2. I'm doing it again. I don't know what's wrong with me. Delta G naught, which means that 298 is delta H not minus T minus 290, God, I'm still doing it again, 298, okay, delta S naught. When you insert that into the solution, what you get is this. Okay, so again, leaving the delta H out of this Gibbs-Helmholtz equation leads to this terrible, gross approximation to delta G2 at higher temperatures. The conundrum is resolved by letting H change with temperature. Don't forget, now this is just a hint to solve the question. You insert this just like I did up there, right? I did the same thing twice. Just want to remind you that once you do this integral, do this, simplify, and then you get the actual correct answer right here. So that's how you do the problem. It will take you a page, maybe two. But remember that I will not put something like that on the test. And I will, because that's a real knocker and will take a while, I'll find a way to make it up for you on the test by a softball question of some nature. Don't worry, you know, even if I wrote a horribly difficult test, I'd just curve it, right? So no worries. Okay, any questions? Right, I know, God, I really talked much longer about than I meant to. The main thing is that if you're a little cross-eyed right now, when you look at the homework, you'll totally get. I'll post it as soon as I get back. I'll post it at 5. Sorry, I'll post it at 5 when I get your homeworks. You'll see it's like question 4. You're going to see this, and this is how to do it. So just so you know that. Okay, that's really all I wanted to say about this stuff. That's law, high school, this college level, especially when you're cursing my name, when you're halfway through a page and you haven't finished it yet. Last bit is actually to go over a little bit of technology, especially because I'm pretty bad about, I do some cancer research, but I'm not a formally trained biochemist. And so I know that I kind of shortchange you on the biochem every now and then. But there is something I do know, but I know a couple of things, mostly about cancer actually. That's largely what I do. But actually there's some technology things I wanted to cover, things that biochemists, if you actually do research in a biochemistry lab, and I do teach the class to make sure that if you want to go to grad school that you can do it, make sure you're at the highest playing field against your other students. Every life's a competition, right? And so I don't want to shortchange. I know most of you won't do that, but that doesn't mean I shortchange the people that do. What I want to cover are calorimeters. There's two things for this. I'm going to cover a traditional bomb calorimeter and show you some neat tricks and tell you a little bit about how people design instruments. I know that's kind of more of an analytical thing, but it's still kind of neat how bomb calorimeters actually work. And then I'm going to cover one that biochemists use to a gigantic extent, and it's really important, especially for drug discovery, and we actually did some development here. Okay, now first is a bomb. Wake up, it's a bomb. A bomb calorimeter, and what's really clever is a lot about instrumentation is just designing a good mousetrap. And what you do with the bomb calorimeter is you have some kind of cup with your chemical, and you have it in a steel container. And typically this is pressurized with oxygen. And around it is a water jacket. So just write that here, H2O. And I'm going to draw the walls like this so that you know that this is actually fairly thick steel. Okay, there's a water jacket. And then there's the, you guys up there. Actually, you know your names, by the way. I think I know all your names at this point. Okay, so then there's actually another water jacket outside of that, but I won't beat you up on it. Okay, so now here's the thing about how clever we are with our technology is, to make sure that we get those numbers in the table in the back of the book as accurate as possible, which they need to be accurate because people design power plants around them, and if you're off even a fraction, that pressure isn't 1 atmosphere, it's 1,000. And hey, guess what? Bammo at 50, or you get my point. You've got to really know what you're doing when you're designing something on a large scale, or people start getting killed. So accurate measurements on a smaller scale are crucial. And when it comes to doing that, people are very clever and very practical. And let me give you one that I tell my grad students right when they first start. Is okay. I've got that now. okay, you've come to grad school and now you need to do a reaction in water, or you're making some standards in water, and so you need to weigh things out. I've got a balance that goes to 5 decimal places. I think there's even balances that go to 6 decimal places. And of course you have a volumetric flask, and now you need to weigh out your chemical as well as you can. You won't be perfectly accurate, that's okay. You know the weight, you add it to the volumetric flask, fill it with water, and now you say, I've made a 1 molar standard. You know, I don't know, you've made a 1 molar, a 1.01 molar standard, right? Because you can't weigh things out. Okay, when a student does it, I say, you didn't do it as accurately as possible. Okay, here's the trick. Now, you use the balance to weigh out the chemical, and the volume, and you put it in the volumetric flask and you added water. One of those steps was actually not as accurate as it could have been. Can you guess which one? Okay, now remember, there's only 2 things. There's weighing out the chemical and using the volumetric flask and filling with water. I contend that one of those steps was actually massively inaccurate. The flask, of course it's the flask, right? It's obviously not the balance. The balance is 5 or 6 places. Okay, now, all right, so I say to the student, no, you didn't measure the volume as accurately as possible. All right, this is like an Encyclopedia Brown thing. It's going to be more my generation. It's little kids' story. Anyway, I've told you enough that you should know that the volume measurement could have been made more accurately resolved. How could it have been made more accurately? Right? Measuring volume. Oh, but you measure volumes in the volumetric flask. There is no more accurate way of doing it. Yes, there is.
Measure the water?
Can what?
Measure the weight of the water?
Measure the weight of water. Because what's the density of water?
1.
1. Right. So the volumetric flask, I don't know how accurate it is. I'm sure it's accurate to maybe like 0.05 mils. But remember, that's 0.05 grams. And by balance goes to 5 or 6 decimal places. That sucker is a heck of a lot more accurate than the volumetric. So you see, my point is that as much as you think of measuring volume, you know, the volumetrics are perfectly accurate. If you just do it a different way, you might be able to gain an incredible amount of accuracy. And this is how you have to think sometimes if you end up designing instruments. And that's the case with the bomb calorimeter. Because it does something really clever. And here's what happens. Let's see here. How do I want to do this? All right, for one, I noticed that this was a steel jacket. And typically these are measured, you don't do formation reactions with these, you just burn things. That's another, you can actually measure thermochemistry just by relationship to combustion H's. Anyway, well, there's other ways to standardize thermodynamics than just formation. But anyway, okay, so delta V is what? So again, I'm going to set off oxygen atmosphere, I'm going to spark it. Anything will burn if you put it in enough oxygen to spark it. What's delta V? 0, right? Because you're in a steel jacket. Okay, now can you get a hint where I'm going with this? So the work is what? Right. You're putting units. Okay, now here's the next clever thing. Okay, so now remember, the innards are actually really freaking heavy, and as much as you've just set off an explosion, it's actually going to heat up kind of slowly because there's a lot of mass. Now, what actually happens on the outside is a temperature that raises. Okay, again, you set off a combustion inside this inner part here. The temperature is going to rise, and so the outside will rise with it. Right? Now, the point is, what do you think the heat transaction is? Negative. Now remember, think about this practically. When I expand the gas isothermally, it's cold because I'm touching it, and heat is coming out of me to keep it isothermal. Now in this case, the temperature of the outside always matches the temperature of the inside. Practically, what's the heat transaction? 0. Right. It's a whole different way to make an adiabatic system than wrapping in glass wool. Because if there's no temperature differential, if when the magic cylinder is cold but I'm cold too, nothing happens. There has to be a temperature difference. It's just a practical thing. There has to be a temperature differential. So notice that you've got a delta U, 0 units. You've got yourself a Joule experiment. You've got yourself a Joule container, kind of. Yeah, kind of. So that's the clever thing. The reason that that's clever is if you consider all of this your system, what you've got is the change in U of the reaction plus the change in U of the water plus the change in U of the steel. These are so thick, these are huge, that you really you cannot ignore the steel. And all of this, now remember, this is the system, it's all zero. Again, units. Okay, now these two, you figure these out by calibration, and of course the temperature is going to change. You did after, it is called a bomb for a reason, but by careful calibration, you know how these change with temperature, and now you know exactly that one because it's just minus that, right? Okay, so now you've got change in U of the reaction. What you always really want is delta H, and that's delta U. Again, you just figured that out. Plus delta PV. But note that this is going to be P delta V, but that's nothing, plus V delta P. So what you've got here, just for completeness, OCD is kicking in. Okay, again, this thing was held constant, so you just got this, and inside the pressure meter, bam, there you go. Now, again, the big picture is that by building these clever mousetraps, it just allows us ways to figure out things with the most accurate tools to get the measurements out to like 0.00001 units of accuracy, which may matter when you multiply the weight of this thing times a million because you're building a power plant, right? Yeah, you see my point? Anyway, look, I don't know that I'm going to test you on this. I did once, 1 year, but anyway, it's just stuff I know that I kind of like to show you every now and then. What is really relevant to a biochemist, though, and this is the thing I typically have added as like the extra credit question, but this is something, if you do biochem, you are going to inevitably see this. It's terribly important to biochemistry because it tells you how proteins interact with proteins and drugs. It is almost universally used for that, and that's called, it's going to take me a while to write it out, differential scanning, calorimetry. And I'm just praying that this is spelled correctly. I cannot spell it all, that's because I'm a scientist. Okay, what this has done is, yes, it's a calorimeter, yes, it's going to be delta H, blah, blah, blah. But what it's really going to do is, beyond that, it's going to tell you when proteins interact with proteins and when drugs interact with proteins. Let me show you how it's built. And of course, there's a little cup with your sample in it. And now, again, this is biochemistry time. And the sample will be water with a protein, and there'll be a thermometer in it. Okay, there's a little thermometer. So just understand that's what I'm drawing. And there's two of them, actually. There's two of them. So one is a reference, and the other is the sample. And anyway, I'm looking these up. And they're just in these little cups. And so I can already tell that that means that we're at constant pressure, which we would want to be. Okay, so it's just in a little box. So I'm just quickly drawing that here. I'm sure it's a nice box, but anyway. And then what's underneath them are heating elements. And I think each one has its own. That's what I was trying to look that up before class. I'm pretty sure that's true. Okay, and what you do is you evenly heat them. Evenly heat the reference and the sample. Okay, now the reference is like, okay, sorry, let me back up. The sample is a protein and probably salt water. A lot of biochemical reactions like DNA hybridization requires a little bit of salt, and that's because DNA is negatively charged. Without a little bit of salt, they just the two strands won't get near each other. They need a little bit of screening. So life occurs in salt water, so the reference is probably just salt water. You need to get that right. It's really important. Okay, and so what you're going to do is you're going to heat them up evenly. But what you're going to find is that you're going to actually have to add more heat to the sample than the reference to keep them at the same temperature. Remember, the point is to keep them at the same temperature. And because of the protein doing stuff that requires delta H, energy, the heat supplied to the sample will not be the same. Now this is how you plot this. So you're going to ramp the heating element over time. And so T is time. I'll write that out here. And what the reference does, being just salt water, it just rises. But the heating that was applied to the sample wasn't quite the same. So this is the sample. And this is the reference. Okay. Now, the trick is that you then convert this to temperature because you know pretty much how it runs. You know the temperature at whatever time, so you convert that to temperature. And you're at constant pressure. Anyone know what this is? What's dq dt at constant P? You've heard of it before. Hold on, let me write it down. Sorry, I should have given myself dq dt at constant P is what? Cp. It's the heat capacity at constant pressure. Okay, so that's what you get out of it. And here's a reference, and here's the sample. And what ends up happening is you just integrate it. And of course, delta H is just the integral of dq over temperature, change in temperature. Okay, so now you've got the delta H. The question is, why the heck is this happening? You know, what is causing the sample to be above the reference to begin with? Let's just say this was a neat protein. By the way, here's a little chemistry E, since I'm kind of just telling you stuff today. That's what I'm going to do today, just tell you stuff. Neat means pure. So I added, if I say, oh, it's just a neat protein, what it means is that I just added the protein. No other protein, no drugs, anything like that. I'll explain drugs in a minute, like I'm not on them. But so what could you guess? What could you guess is causing this to happen, again, if I just added a neat protein to the sample? What kind of process could a protein go under that ate of heat?
Denaturing?
Denaturing, right. You are measuring the denaturing temperature. That's what you're seeing. And later, the last day of class, I'll tell you a little bit about how we figure out how proteins denature and things that we do on a computer, by the way, because, well, anyway, that day will come. What's really neat about this, though, is kind of like, well, yeah, we can test our theories and our computers on how proteins denature. Proteins denaturing is kind of important. You know the prions that give you mad cow disease, and we're all predicted to die of mad cow disease a couple of years ago. I mean, that was the thing to be scared of, and then ISIS came along. But anyway, that's our government. But anyway, I'm going to disappear tomorrow. Right. Okay, so you know that prions actually reform themselves. They're actually catalyzed by other prions, and so when that happens, they tend to fall out of solution. Oh, I remember this is like a chemistry Olympiad question. Is boiling an egg a chemical change or a physical change? Any of you? It's a physical change. It's protein denaturing. It's technically a physical change. So denaturing is important. But let me tell you why you really want to do this, and I'll correctly label this as CP versus T. Here's why you want to do this. Let me do the reference, and here's the sample. Okay, and let's say that this is a protein. Let's say this is a kinase, and I barely know what that is. I think that's a protein that phosphorylates things on the surface of a cell, and when that happens, the structure of the protein changes. That's what phosphorylation does. When the structure of that target of the kinase changes, it tends to makes the cell do things like grow faster. Okay, well, cells need to grow. If they don't, though, but they grow anyway, what do you have? Cancer, right. So sometimes, if this protein is a kinase, we might want to shut it off. Because if it's a kinase and it's overactive, it's causing cells to grow when they shouldn't. That's cancer. Okay, so this is the protein denaturing. Now let me draw the protein this way. We all know that proteins have complex structure. And these are all the, folds and alpha helices and beta sheets. I'm just drawing something funky. And again, this is a bad protein, and I'm trying to figure out an inhibitor, a kinase inhibitor, that will stop this protein from causing your cancer to grow. That would be a good thing. What you do is you start adding in drugs, and very cartoonishly, the drugs are like this, they're like that, they're like this, and they're like, I'm just making stuff up. Which one works?
The one that fits.
This one, right. That one works. Okay, it's binding to the protein. And guess what's going to happen to the denaturing temperature? It's going to go up. Right, you see, because remember, protein, you know this, protein denaturing is the protein falling apart. But if it's interacting with the drug, that's a little bit harder because it's got a little mortar to the bricks. And that's going to raise the denaturing temperature. So in other words, take this protein, and we have what are called libraries that are like 10,000 organic chemicals. Several are organic chemists, they do nothing. But they like invent a reaction, they generate 10,000 new molecules with it using machines. And then they take those 10,000 things, add it to a protein like a kinase that causes cancer, and they look for this behavior. Once they see that, then they take that's a candidate compound. At that point, they start doing more tests, and that's how they do drug discovery now. So yeah, that's why this is horribly important. There's actually a way to do this even a little bit easier. Instead of doing this in a calorimeter, a DSC, differential scaling calorimeter, you can actually look at the fluorescence. What you can do is actually add a fluorophore to a protein, attach a dye to it, and what will happen is the dye will only become bright if the protein denatures, and it's dark if it doesn't denature. And so instead of even putting this in a DSC, you can just label the protein and look at for what temperature the dye suddenly turns on. Anyway, don't even write that down. It's just, there's more ways to do this than just the DSC. And actually, I remember Leslie Fung was a person who's a developer on this. So anyway, big picture is, this is why thermochemistry is important. This is how biochemists do it. This is why they do it. And it's kind of important because, like, I can tell you one of the biggest miracles in cancer right now is Gleevec. I don't know what it is. Chemically, I don't know what it is. It's a cancer drug. Gleevec and one other. So when you used to get lymphoma, which is a blood cancer, there were certain, actually almost all of them, you're dead. I mean, it's automatic metastasis, so that's when cancer is everywhere. If it's in your blood, if you have blood cancer, you have cancer everywhere. You're not going to live. But Gleevec comes along, right? Someone discovered drugs this way. These new drugs came along, and if you get the right kind of lymphoma, you can take this drug. You have to take it for life. You will live. Right? Normally, you're not going to survive long at all. But because of the way we do these drug discoveries, this compound comes around. It's actually, I know two people on it, and they will be on it the rest of their lives. It's not pleasant, to be blunt, but otherwise you're dead. So go to grad school, right? Go to grad school, do this kind of work, because cancer is awful. 1/3 of you will get cancer. Heart attacks will get most of you, but 1/3 of you will get cancer. And this is how we're going to stop that from happening. Okay, last bit, folks. Let me start on a new subject. I'm not going to get that far with it. Okay, you're all a little randy today, probably because you're on drugs. Let's drop all this right now and go to a new subject, which is open systems. Okay, so I'm kind of dropping the Hess's law, and I'm going to come back to it. Come on, folks. Give me just 5 minutes, right? Then turn in your homework. I'll return your homework. So actually, let me just introduce one simple thing here, and then actually I'll save it for Friday, which is, and I kind of hate to do this to you, but let's write the change in U. And by open system, by the way, I'm not referring to, here, let me just write this out. I'm not referring to the magic cylinder with a hole in it. That does actually work. But when I say open system, I'm going to actually talk about a chemical reaction. So the magic cylinder is still closed, but the reason that it is an open system, before all our magic cylinder stuff was closed, and that just meant that N, which you always kept constant, was still constant. Now in an open system, the magic cylinder is still sealed, but N will not be constant because a chemical reaction is occurring, right? So that's the definition of open system. The way you do the thermodynamics is you need to take into account the change in energy, and you're going to have to hold the other variables constant as the number of moles change. Okay, that's how you deal with it. And it makes sense. Remember that energy is extensive. More molecules have more energy, unless you're at 0 degrees K, and why would I worry about that? So if you're going to, if the magic cylinder suddenly has more gas inside of it, again, because a chemical reaction occurred, it ought to have more internal energy. That just makes more sense. And the same with G, minus SDT plus VVP. Yeah, I got these memorized, but remember it's on your, it is on your cheat sheet, which I will send on Wednesday. This is a function of T and P, Pn. Okay, now the reason this is important is that, remember I've been saying that delta G, we want delta G to be negative in a constant temperature pressure world because then the total entropy increases, right? Right? You know, you didn't get that in high school, but now you got it. And at this point, hopefully you're like, yeah, whatever, I got that. Do you? Because at constant temperature and pressure, what's delta G? Seriously? 0. But I told you it had to be negative, but there was no way for it to be negative. From what I told you, you just accepted it. You should feel bad. Right, the answer is because of this term that I just hadn't shown you yet. To be honest, there's actually other terms. There's surface. These DGs and DUs and DHs, in honesty, they go on forever. I'm just showing you the most important ones. And now that we're doing reactions, there's another one. There's even a term for surface energy, surface tension times area. Other stuff I don't even know. Electrons, I think. I don't know. Look, these do go on forever. But for the most part for this class, I've shown you this, and now I'm tacking on this, and I'm going to stop there. In terms of adding things, no. In terms of adding things to U and G, just wait 1 second. Okay. One thing I want to point out actually is I do have enough time. This is a homework question, so let me show you how to do it. Which is that as much as you've had to remember rules for changing U and changing G, and of course there's ones for T and S and P and V, it's like I've added a whole nother one. A whole nother group of P's and D's and T's and Legendre transforms amongst them, yes? Yes and no, and for this reason. Let me point out that DG is DU minus the change in TS plus the change in PD. Okay, I want to point that out. Now, the point of this is to show that actually, as much as I've just tacked on another term, and it's like I've maybe like squared the complexity of all these derivations, I haven't. I'm explaining that. Okay, let me write down DG minus, and I'm going to do this right here. SDT plus VDP. Sorry, I'm going to kind of run out of room here, so this is a little funky. T and P. Okay, so I just wrote DG. Now I'm going to write DU. And again, that's to my left. Nothing weird. Change in U, change in N. Got to remember that S and V are held constant. Now I'm going to add the change in TS. And, sorry, I'm going to subtract the change in TS, my bad. And then do the plus the change in PV, PDV plus VDP. Okay, I'm sorry this is stretching across the board. I should have started the new board, my bad. Okay, let me point out some things. Let's see. That's gone, that's gone. As you know it should. That's gone. Okay, what I've got is change in U, change in N, SV, DN, plus VDP, minus SVP. Sorry, I got them out of order. And I've still got the same here. And hopefully you already see what I've done here. If not, I'm just going to write it down in a second. If I'm going too fast, just watch the video. Look at that. They're across the aisle. The same terms are across the aisle. And therefore, the change in Gibbs energy at constant temperature pressure is actually equal to the change in U as long as S and V are constants. Okay, so here's the point. As much as I've unfortunately just complicated every freaking thing we have done by tacking on one more term that I could do Legendre transforms with, and yeah, I will, like on the test. Actually, it's not that bad because every term I tack on is actually the same. And these are called chemical potentials. Like you heard about a little bit in freshman. Okay, chemical potentials define when things react and how much they react. So that's how you're going to figure out extent of reactions and yada, yada, yada. So anyway, with that, return your homework.